Hi everybody. So this week there's just a couple more lectures on quantum mechanics, and these lectures are going to explore the nature of quantum particles in a little bit more detail. And in particular we're going to focus on looking at this wave-particle duality, this idea that in certain circumstances these quantum particles behave like we understand classical particles to behave, like they're just like a point that moves around. And in other circumstances, they behave in the way we expect classical waves to behave. For example, they show diffraction and refraction effects. Okay, and then how can we combine these two different things into a single description of a quantum particle? Right, so this first lecture is covering a thought experiment known as the double slit experiment or the Young slit experiment. And it's basically a simplified, abstracted version of this diffraction experiment for electrons we talked about in the previous lectures. So just to remind you what this experiment was showing, this is showing that electrons in some cases can behave like waves. You pass a beam of electrons through a very thin foil, which acts like a diffraction grating, and you find that when you look at where the electrons arrive at the screen on the other side of the foil, you see these circular patterns which can be easily understood as a diffraction effect if you model the electrons as being waves. Okay. So this is evidence that electrons sometimes behave similar to classical waves. Right, so this is the double slit experiment, which, as I said, is like an abstract, simplified version of that experiment. You start off, you have a source down here, which can be a source of electrons or a source of light, like photons or whatever you can choose. And the source fires out these particles in a certain range, and in particular, there's a significant probability that particles can go through this slit. Slit is like a little hole here, or this second slit here. So it's called the double slit experiment because you have two slits the particle can go through, one through here, one through there. Okay, and after the particle has passed through the slits, you detect where it arrives at a screen behind the two slits. Okay, so in the real experiment, this would be the aluminium foil and this would be the detection screen, but now we've made it one-dimensional and we have just two possible places that the particles can pass through. Right, so this presentation is going to describe what you would expect classically from particles and waves, and then we will see how we can combine these descriptions to make a description for these quantum particles, these electrons. Okay. So first of all, this is a picture for classical particles. What would you expect to see? So here the source is like some sort of gun and it's firing particles in a range of directions. So many of these particles will just hit the wall and stop, but some of the particles will go through one of these slits. Now, if first of all we look at the case where only one of these slits is opened, we close the other ones, then as the particles go through the slit, they can, be deflected by some angle, and you will get some distribution of particles arriving at the screen that looks something like this. Okay, so here P1, this is showing you the probability distribution for particles going through slit 1. Okay, slit 1 being the slit here. Right, this is slit number 1, this is slit number 2, which is closed in this first picture. Okay, so there's here this large amplitude means that you have a high probability of particles arriving at the screen here, and here a low amplitude means you have a low probability of particles arriving at the screen up here and down here. Okay, so hopefully that's clear. Right, now if you do the same experiment with the second slit open, then you get exactly the same picture, just a mirror image. Okay, And now if you do the same experiment with both slits open, then you just add the two images together, right? So for each particle, the particle either goes through slit 1, which will give you the first probability distribution, or it goes through slit 2, which will give you the second, and if both slits are open, you just add them together. Okay, so in particular with both slits open, the probability of detecting a particle at x is equal to the probability if it went through the first slit plus the probability that it went through the second slit. Okay, so here P12 again is the probability to detect the particle at a particular position x along this screen when both slits are open. So 1, 2 here means both slits open, whereas P1 is with only the first slit, P2 is with only the second slit. Okay. Right, now if we look at the same picture but for classical waves, then firstly you must measure something different, so you're no longer measuring the probability of detecting a particle because these classical waves are continuous things. So instead what you can measure is the intensity or the energy of the wave at a particular point on the screen. Here E1 is the energy or the intensity of the wave at point x. So here this is a function of x on the screen. Okay, and as before, the 1 here denotes that this is a wave which has gone through the first slit. Okay, and we get a similar function for E1 as we did for P1 for the case of classical particles. The wave is most intense, has most energy at a point which is closest to where the slit is, and then as you move away you get lower intensities, lower energies. Okay. Right, and if you have only the second slit open, you get again the mirror image of that picture. But now if you open both slits at the same time for waves, then you get a very different picture. Okay, so just to talk through what's going on here, so these lines here denote places where the wave is up. Let's say like the wave is going up and down like this. You can see there are certain places where these two lines intersect. So here you have one wave coming out of the second slit like this, another wave coming out of the first slit like this, and at this point here where the lines intersect, that means both of the waves are in the up phase. Okay, so here and here and here and here and here and here, you can see that all of the waves are in the up phase, and in particular everywhere along this line the waves from both slits will have the same phase. Okay, so this means they will add together and you'll end up with a very large amplitude or a very large energy here. So here you have constructive interference. Okay, you can see there are some other lines that are similar. If you look at the next points here, we have a point there, point there, point there, point there, point there, and point there, so on, where all of these waves are in the same phase, and again that will get you this second peak here. So this is also a constructive interference peak. But in between them we have places where, if you look somewhere like here, so in the center of these two lines, that corresponds to a point where one wave is in the up phase and the other one is in the down phase, right? So here, 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 you will get destructive interference, and that will take you to a point where the intensity, the energy, is very low. Okay, so because of this interference effect, you get this rapidly oscillating pattern on the screen, which will give you the diffraction fringes, which are a result of the interference. Okay, and note, because of this interference effect, it is no longer true that the energy of the waves with both slit open is going to be equal to the sum of the energies when you have only one slit open. And that's no longer true because you have interference between these two waves. Okay. Right, so when you do the experiment with electrons, you see exactly the same diffraction pattern as you do for classical waves. So obviously the electrons are behaving like classical waves in this sense, but because the electrons are particles, right, it's possible to do the experiment where you send through the electron, just one electron at a time, and you measure where it hits the screen one electron at a time. So rather than measuring the energy or the intensity of the pattern here, you can actually just measure the probability of an electron hitting a certain place in the screen. Okay. So if I just fit this up here, if we do this experiment for electrons, then because these are discrete particles, we can measure the probabilities of arrival at a certain place. As we did for the classical particles, but the result with both holes, both slits open, P1, 2, shows interference similar to the classical wave picture. Okay, so this is what we need to understand. Right, so before I talk about electrons, I just want to introduce some mathematics for how we can quantify these interference effects which give rise to the diffraction pattern shown for classical waves. Okay, so how can we describe a classical wave? Okay, so if I were to plot what a wave looks like, so this could be like a wave in water, or it could be the electric field in a light wave. It has a, say, sinusoidal shape which looks something like this. So here this is x, and here we are plotting the amplitude and phase of the wave. So this oscillating pattern here is some function a, which is a function of position x and time t. Okay, and the amplitude of the wave is the maximum height here. So this is going to be the amplitude, which we can say a, and a will in general depend upon the position you are on the screen. You can have different amplitudes at different places. Okay, then the wave can be described like a function a xt is equal to a of x. Well, I've written it as sine, but let me write it as cos for a reason you'll see in a moment. Cos omega t plus some phase phi, which is a function of x. Okay, and we can write this down as ax times the real part. This is why I write cos instead of sine of e to the I omega t plus phi. Okay, so this phi x here is the phase, and this is what determines whether your wave is going to be up or down. Okay, like this. Right, so for a classical wave, when we measure the intensity, so that's the energy contained in the wave, the intensity is proportional to the amplitude squared. Okay, so for example, the energy contained in a light wave is proportional to the amplitude of the electric field squared at that particular point. Okay, and this therefore is the absolute value of the function axt. Okay, no, I can't write that. It's the absolute value of the function a of x times e to the I omega t plus phi x squared, right? Simply because this thing here has absolute value modulus 1. So it doesn't change anything. Okay. Now, if we consider what happens when two waves overlap, okay, so we consider we have a first wave described by a1 and x and t, which I'm going to write as a1x times, again, the real part of e to the I omega t plus phi 1x, and a second wave, a2 xt, which is a second different amplitude times the real part of a function that looks like this. Okay, so here a1 and a2 are describing the waves from the first and second slit in the experiment. Okay, so if I go back, sorry, here, then we would say that this wave here is given by the function a2 xt, and this function here, this wave here, is described by the function a1 x and t. Right? Okay, so then in the final picture we add the two together to get this interference pattern. Okay, so the total wave is going to be a1 xt plus a2 xt, which is the real part of a1x e to the I omega t plus phi 1 plus a2x e to the I omega t plus phi 2, and therefore the intensity of this wave is going to be its absolute value squared. Okay, I have to write the whole thing again. Let me just copy and paste it to save a bit of time. Okay, so the intensity is the absolute value of this thing squared, and when you calculate what that's going to be, you get the first term, which is just going to be a1 squared. You get the second term from here, which will just give you a2 squared, and then you get the cross terms where you multiply the first term here by the complex conjugate of the second term here. Okay, so that will give you a1x, a2x, so you will get e to the I phi 1x minus phi 2x. And then you'll also get the term when you multiply this second term with the complex conjugate of the first term, which will give you e to the I phi 2x minus phi 1x. Okay, and then using the relationship between complex exponentials and sine and cos, you see that this can be written as 2 cosine phi 1x minus phi 2x, like this. Okay, and it's this term which gives the interference. Okay, the first term is just the intensity of the first wave squared. The second term is intensity of the second wave squared, and this term therefore describes the interference, which gives you the constructive and destructive peaks and troughs in E12. This one is proportional to E1, this one is proportional to E2, and this term here describes interference. Okay. So to get the interference, what do we need? So the first thing is we need to have a wave which is described by an amplitude and a phase. Okay. You need that if you have two waves together, then you add the amplitudes for each wave together like this. And we need that the thing you're measuring, the intensity, is proportional to this total amplitude squared. Okay. So in summary, to describe the interference, we need the following effects. So the first one is a wave with amplitude and phase. Okay, which is what I described by this function a of x and t. Okay. Secondly, you need the fact that if you have several waves, then these functions are added together. Okay, so you add them together like this, a1xt plus a2xt. And the third thing is the measurement, which in this case is the intensity of the wave, should be proportional to the absolute value of this squared. Okay, right, so given that we have exactly the same interference pattern for electrons as we have for classical waves, we can say something then about how we need to describe the electrons. Okay, so firstly we need to describe them by some sort of wave function which has an amplitude and phase similar to the case of the classical wave here. Secondly, if there are two different paths for the electron to go through, then we need to add those amplitudes from the two different paths together. And finally, the thing we're measuring needs to be proportional to the absolute value of this thing squared. So to get an equivalent description for the electrons, we need, okay, so I'm just going to do identical points 1, 2, 3 to the ones above. We need that the electron is described by a wave function, as it's known. AXT. Okay. Secondly, in the case where both slits are open, the wave functions are added together. So if there's more than one possible path, the wave functions for each path are added together. Okay, just as above. So if we have two slits open, then the wave function for the electron is the sum of the wave functions for it going through the first slit and the sum and for the second slit, like this. And finally, number 3, the thing we measure, which is now the probability to find the electron, is P. So in the case of 1, 2, P12 x and t, this is equal to the absolute value of these two wave functions added together. Okay. Right, so if we combine all of these 3 points together, we can get in exactly the same picture for electrons as we do for classical waves. But notice the critical difference is in terms of what you're measuring. For a classical wave, you're just measuring the intensity. That's the total energy contained in the wave at a particular point. But because electrons are discrete particles, you can fire them one at a time, okay? And you measure them just one at a time. So you can't measure intensity in a continuous sense anymore. So instead, you have to do the experiment many times with many electrons and instead measure the probability of detecting a particle at a particular position on the screen. Okay. So this should remind you of what we saw in the Stern-Gerlach experiment when you measure the angular momentum. Again, the quantum state is defined in terms of probabilities. It can tell you the probability that a particular measurement will be at different points on the detection screen. But in order to see that, you have to repeat the experiment many times. Okay. And the same thing is true here. For one electron, the quantum description, these wave functions, only tell you the probability of where the electron is going to hit. It can't tell you exactly where. And to see this probability distribution, you have to repeat the experiment many times with many electrons. Okay. Right, so if we go back to the picture here, note that this says something very interesting about the way the electrons behave. You get exactly the same interference pattern even if you only have one electron going through at any one time. So that means you cannot consider electrons in terms of particles like this. For example, suppose that I did this experiment with a single electron and I detected it here. Then in order to correctly calculate the probability of the electron hitting the screen here, we have to consider simultaneously the wave function for the electron going through the first slit and the wave function for the electron going through the second slit. Okay? So we cannot say the electron went through slit 1 or the electron went through slit 2. Right? The wave function for the electron went through both slits simultaneously. Okay? So therefore it's impossible to think about the electron as a localized particle. right? You have to consider the wave function for the electron going through both slits in order to get the correct answer in the experiment. Okay, so that's a detailed description of the two-slit experiment, and it leads to these very important concepts which are key to quantum mechanics. Firstly, this description of a wave function for the electron is fundamental to how particles are described in quantum mechanics, and this is going to be the subject of the next video. And secondly, this relationship between the wave function and the probability of detection of a particle. Okay. So probably that's important, so I should probably summarize it again down here, I think. So the quantum state of the electron is described by a wave function which I have called AXT here. Quite commonly the symbol psi is used for wave functions, so if you read quantum mechanics text you may well see the symbol psi here, but it means exactly the same as what I've called A in this lecture. And secondly, the wave function is related to the probability to find a particle at a particular position. So to the probability to find the electron at a particular point. So in other words, the probability to find the electron at point x at time t is equal to the absolute value of the wave function at that point in time squared. Okay. Right, so that's where I'll finish this video, and in the next video we're going to talk more about these wave functions and see the effects they have in terms of quantum measurement, and see how we can understand this wave-particle duality in terms of these wave functions.